All right, so we've made it to part 4. By the time we've gotten here, we actually know everything we need to know about ER diagrams and entity relationship notation. It's still pretty tough to actually get used to designing data models using this notation, but the point of part 4 is to describe the conversion of an ER diagram into a set of create statements for SQL tables. Now what that means, because we actually haven't spent much time using SQL tables, is you'll have to take my word for it on a couple of these things, and we'll just have to sort of leave this as a placeholder for later. So it's a significant thing, but this is mostly a postscript. It's mostly an epilogue to all of the ER stuff that we've been doing. It's a way of tying it in to what's going to come next in the course. So first, let's remind ourselves briefly. So there was a recorded lecture about this a couple weeks ago, but we use this statement create in SQL to first create a table. And we know that it contains, that when we create a table, each table contains a bunch of columns, and we specify them. The sort of declaration of a column type is in the opposite order that we expect from things like C and Java. So it's first the name of the column, then the type of the column. We have two ways, so a create statement can contain a variety of other things besides just names of columns and their types. We have two ways of indicating, for example, what the primary key of the column is. So we spent a lot of time talking about candidate key and primary key, but in the context of ER modeling, all of those underlined attributes we were talking about in part 3, that's the primary key. There might be more than one way of defining a key, but all we care about now is those underlined attributes. That's the key that we've chosen. Unlike in the discussion of normalization, where the different keys are significant, here, when we're designing from the top down, when we're implementing these tables, we just take the key that we've defined when we were designing the data model, and that becomes the primary key. So the question is, how do we tell the database that? And we need to do this for a variety of reasons. The biggest one is that we need to enforce constraints between tables. A secondary one, which will be more important later in the course, and certainly is more important in practice, frankly, is that we need to be able to quickly search the tables. And usually the database will understand that the primary key is significant in defining the elements of a table, and therefore optimize the table storage to make it easier to search the table using the primary key columns. We're actually going to come back to this at the end of the course as well. But from the point of view of implementing a data model that's faithful to the data, the uniqueness of the key columns and the ability to tie tables together by their keys is the significant thing that we care about. So one option is to choose, if we have a one-column key, like student ID is our key, we can put the words primary key after it, and that defines a single-column key. We also have the option of, after the end of our list of columns, so after that last comma there, we can just write primary key and then in brackets a list of the key columns in no particular order for our purposes. We actually can do that for single column keys too. So if you'd rather not use this notation, you don't have to, but you should learn to use this notation because you do need it for multi-column keys. Here's a wall of text. I apologize in advance for, I think this set of slides has a whole bunch of these cases where the text runs really close to the bottom. Sorry about that. Whenever I put a primary key directive in a table, a create statement in SQL, I am telling the database to definitely enforce the uniqueness constraint. Database systems typically, by default, will actually let you put, in a table with no keys, they will let you put duplicate rows. And this is a weird implementation trade-off that we have to deal with, where the SQL will let you break the relational model. If we put the primary key directive in, and spoiler, you're always going to be required to do that, if we put a primary key directive in, even if we have to put it in for every column of the table, it's required in this course. Once it's in there, the database will enforce that no two records in the table will have the same values in all key columns, which is exactly the same as enforcing that constraint that we've always assumed to be true on keys. You might think that's a bit backwards. Like, why do we care if it's doing that? Because we know no two rows will ever have the same value in all the key columns. Well, of course we know that, but that's not preventing somebody from accidentally inserting an invalid row. So if they try and do that when SQL is a primary key defined, it will reject the insertion. It'll say, sorry, this is already there. And this describes both the reality of the situation and what I just said, which is that you must define a primary key directive. We want to keep our tables strict to the relational model. Now, this also mentions that when you define a key, and this will actually spend a significant amount of lecture time on this late in the course when we talk about database indices and optimization for storage, The database will interpret the key because it's a defining attribute of the data. It'll interpret it as the best way to organize the data. And that turns out to really help us when we need to do operations that search the table by its key. So that includes basic things like give me the name of the student with this student ID, where student ID is the key, or an operation like a join, which usually uses the key as part of its join criteria. This is one reason why surrogate keys can tend to be a bad idea if they're not justified. Because that means if the meaningful part of the data, the meaningful characterization of the data isn't its key because you've defined a surrogate key, then searches that we do on the meaningful aspects of the data are slower because the surrogate key is the one that's been optimized for searching. We also need to talk about this. This is going to be, for a lot of people, a really weird adjustment because I'm saying refer to, and this means something specific. If a table contains columns that are meant to refer to the columns of to the key of another table, then it's what's called a foreign key. So that doesn't mean every time a table contains a column called student ID, we should link it up to the student's table with a foreign key. It's only if the meaning of that is the same as it would be in the other table, usually because we have defined some sort of relationship. And here we've defined a very basic one. So I have this table called departments with an attribute department name. And you might notice that in the students table, I have an attribute called department, not department name, just department. But suppose I've decided as the database designer that the attribute department, is meant to refer to the name of a department as stored in the departments table. And we'll see that that's obvious because there's actually going to be a relationship on my diagram that says that. If that's the case, then I am referring to the key of another table, and so I add the foreign key. I do not do it every time I see this. I could have in some other table elsewhere in my database the word department meaning something completely different, like the fire department or a province in France or something. Just because it has the same name as a column doesn't mean it refers to the key of another table. In this case, though, the department that the student is in logically is the department on campus that would have a particular name or location or whatever. So logically there, I'd want to define a foreign key. So when I have columns in one table that refer to the key of another, not just by name, but meaningfully refer to it, then I define a foreign key. That is one way to make sure that I have what's called referential integrity. So what I want is if a student has a particular department in their record, like math, I want to make sure that math is a real department. I want to prevent you from adding a row to the students table with a department name that doesn't exist. So what I do is add this foreign key constraint, which every time I try to insert a row into the student table, it'll say, oh, math, huh? It'll go looking for something in this table with the record with department name math. And if it doesn't find it, the constraint isn't met. So a foreign key is a way of enforcing that we have consistency between tables where a linkage legitimately exists. I'm allowed to add as many foreign key constraints as I want, so I could add a stack of them, one for the department, one for the student ID. I could also, if I wanted to, have part of my primary key or all of my primary key for the table be a foreign key. That's valid. So there's no requirement. In fact, arguably, the word key here is often misinterpreted. The idea is this is the key of a different table. It doesn't have any implication on whether this set of attributes can be the key of this table. It can or it can't. It's up to me. So let's try this. I have now my fleshed out student course instructor example from before. We'll see there are the keys. I've grudgingly added my surrogate keys. This doesn't need a surrogate key. I use the course code. Let's turn this into a set of tables in SQL. So what I want ultimately will be I'll turn each entity into its own table for the most part, and then I will turn each relationship into a table that bridges between two entities and also contains whatever other attributes like grade are attached to the relationship. So before I do any of that, I have to actually find a way of turning these abstract representations of attributes like name and address into typed data, because SQL is a typed language. I'm actually not going to bore people with that in this recorded lecture. I will post to Connex a set of notes about SQL types, or links to data about SQL types, the basic types that you will be using in this course. For the most part, the basic types are sort of obvious. The names are weird, but the types themselves make sense. The exact names of types and set of types available in each database engine is different. It's actually not standardized. And so that's one reason we shouldn't worry too much about it, because it'll change if you go out and work on databases elsewhere. It'll change a bit. So instead, we'll play that by ear. You won't be tested too much on the types, and you'll be given a decent amount of warning. But as you've seen from the first exam, because you're allowed to consult resources, I'll post some resources on types and you can take a look at them. Really, we care about the usual typing issue we have with languages, which is, do we want an integer or a real number? So instead of float or double, we say real in SQL. Do we want to store strings, which we typically use this type for, varchar, which would be a variable length character record. We don't have a general string type in standard SQL. And there is a type called char, which allows you to make a fixed width string, but we don't generally, these days we like to interpret strings as being in the same vein as they would be in Python or Java, which is variable length. Well, notice the SQL varchar type has this annoying limitation of requiring a maximum possible length that we specify, which causes us no end of concern for issues like, what's the maximum length of somebody's name going to be? Is it 100 characters? Is it 1,000? There are also types for things like dates and times. In the slides, we're just going to use a date type and not talk too much about it. As we go forward, just bear with me on that. In the course, it'll become obvious when we're working with dates when we aren't. I'll post notes as needed when we get to weird exotic types. For this diagram, fortunately, it's pretty obvious. We're working mostly with strings. I mean, this is a number, and I guess these could be numbers. Although if we're representing them, like the UVic style student IDs, like this thing, I'd probably, even though, yeah, it's a number, I would store that as a string. Because who's to say that we don't change it to be W00 tomorrow? So it's better if you have something that's string-ish to probably use a string for it. So I probably can use grade as a number and just about everything else, maybe not ID. Everything else can be a string. And so just, the disclaimer here is, look, if you want to talk about types, take a look at the notes. It's hard to give a remotely interesting lecture where I just list types. So first, I've chosen types for everything. I haven't written them down yet, but I also now have to, once I know the types, I will create a table for each entity. I don't have to call the table course or instructor. I can make my own decisions about what to call tables, and I will have to take some liberties with naming later on. So once I know the type of everything, I can make a table for each entity. Here, though, I think student and instructor, those are pretty good names already. And I'll add the primary key directive as needed. So here I could say courses. Generally, our entities tend to be named with nouns, but the singular noun makes sense for the entity on the diagram. But, course as a table, I want to be able to say stuff like select name from courses, the table of the courses. So I tend to pluralize things. And so, okay, the name, the code, and the department are all strings. I have decided this is not a good idea in general. I've decided so varchar 50 means a string of length at most 50. Now, some database engines don't actually enforce that, but we should try and choose reasonable numbers here. A person's name or a course's name, let's limit it to something choose a very high upper bound, maybe 1,000 characters. It won't always allocate 1,000 characters. Internally, the database engine probably uses null terminated strings or something. But it's better to play it safe. You don't want to end up with a course whose name is like 100 characters and then have to go back and redesign your database. So it's better to choose something on the safe side. So I wouldn't, even 50 is a bit too low here. For the course code, 10 might be reasonable, because if we look at course codes in UVic, they're going to be a 3 or 4 digit department code like CSC or SENG, then a space. So now we're up to at most 5 characters, and then a 3-digit number possibly followed by a letter. So 370 or 485B or something. So 10 might work there. There's no reason we couldn't just say I don't want to worry about it, so I'll make it 20 or 30. And then department name, okay, 100. But so you're not tested on choosing the right numbers for these for the most part. Like I guess there could be like one question about that. It's usually just a case of always err on the side of caution. So I could also make tables for students and instructors. But use your imagination. For now, we'll just do courses. And then for each of my many-to-many relationships, so we'll see later we have to do different things for one-to-many. For each relationship like this, teaches or takes plus grade, I create a table. And the table I create for, let's say, the takes relationship will contain all of the key columns of each end of the relationship. So takes bridges student to course. So I'll include the key for student and the key for course, as well as whatever is attached to the relationship. Now, the takes relationship reads well in the diagram. A student takes a course. I don't want to call a table takes. That's going to be really annoying later. Instead, I'll make up what I think is a reasonable name for it. The slide agrees. So I'm going to call it enrollment. So what I've done is I've pulled in the ID field from the students table. Now notice how I don't call it ID, I call it student ID, because in the context of enrollment, I don't want there to be any confusion. Student ID is a number, course code is a string, and then grade, at UVic grades have type int, so grade is an int. Then I define the key for the table, and the previous slide lists that. The key for the relationship table is the combination of the keys of all the entities. It does not include the attributes of the relationship. So here the key would be, well, the key of the student table is the ID, the key of the course table is course code. And then I add foreign key constraints because these columns here do refer to the keys of other tables. And in this case, in the students table, I just called it ID. In the courses table, I just called it code. But I'm allowed to rename it, so I just write, well, hey, student ID refers to students, column ID, and course code refers to courses, column code. So I am allowed to disambiguate, and I really encourage that. If I just called these columns ID and code, and then I handed you the enrollment relationship, you would look at it and say, what is ID and what is code? But if I tell you student ID course code, you don't need to know anything about the student table or the course table to get some idea what this table contains. And then final point, just to reemphasize this, notice that the primary key of my table is only the keys of the things joining to the relationship. It is not whatever attributes the relationship contains. Those are just along for the ride. Okay, so let's try this one. So here we have these many-to-one relationships. So an order is sold by exactly one sales rep. An order is placed by exactly one customer. Now, it turns out we could do the same thing as before, but it doesn't help us too much to do that because we want to have the database sort of prevent the many-to-one constraint from being violated. Ideally, we want it to be impossible for there to be any more or less than one customer per order. And you might notice from this representation, I could choose to add a given student and course to the enrollment relationship or not. Or, there's nothing preventing me. I can't add it twice because the primary key constraint will prevent that, but I could add it 0 times. I want to encode these constraints into my tables such that it's impossible to violate them. We know from discussing normalization that if all goes well, we can design a system where we don't need to do any extra work. The structure of the system does the work for us. So in the case of these strict, so rounded arrow, many-to-one relationships, we don't actually need a separate table for the relationship. It turns out that if you think about it, every order has exactly one associated customer. Well, why don't I just throw in the name of the customer or the ID of the customer with the order details? Why do I need a separate table to store that? Same with sales rep. Every order has to have a sales rep. Why not just throw that in when I describe what the order looks like? And so the way we do this is to make a table for an entity that has many-to-one relationships, like order. We add the columns like we otherwise would, ID and date, and then we pull in the keys of everything with a many-to-one relationships, everything on the other end of the rounded arrows. We end up with this. So for the sake of, because now order will contain an order ID and a sales rep ID and a customer ID, we have to disambiguate. So I will call the key of the order table order ID, and then there's the order date. It's a date, whatever that is. And then I will bring in the ID from the customer table. We'll call it customer ID, even though in the customer table it might be called just ID. I can bring it in and rename it. And then the sales rep ID I'll call sales rep ID. To make my life easier, it's nice to have descriptively named columns. My primary key is now just the order ID. Notice that I could have written this with a directive after the order ID column, but I chose not to. And then I define my foreign key constraints to enforce referential integrity. So the goal, again, of these foreign key constraints is that if I attempt to add an order with order ID 1, order date 5/26/2020, and customer ID 3 and sales rep ID 97, I want to make sure that there is a customer ID 3 and a sales rep ID 97. And these constraints will make the database go check. If I attempt to add this row to my orders table, it won't let me unless that's a valid customer and valid sales rep. It enforces the integrity of the data. If I don't have the foreign key constraint, it doesn't know about that relationship, and so it doesn't try to enforce it. So I could end up with strange, like dangling loose ends in my data. So what about weak entities? So it turns out that actually we sort of get this for free if we know about how to handle this thing. So we know that every weak entity comes with a rounded arrow on its supporting entity. So a county is part of exactly one state. And the way we define the table for county is we do the same thing we did before. We just pull in the key of everything at the other end of the rounded arrow. The difference is that part of the foreign key that we bring in will become the primary key for my table. So here, okay, I've got the county name, I've got the number of voters, I guess, and then I have the state name, which I have brought in via this foreign key constraint. I've brought it in from the states table. And the primary key is then the combination of something I have locally, the county name, and something I pulled in from somewhere else, the state name. So I am storing the state name in the counties table, but I'm forcing it to agree with the state table. It's redundancy that I can't avoid because I need some way of linking those two tables together, but the database is enforcing that the redundancy is consistent. Okay, so what about this? I mean, this is a pretty mechanical conversion. All we need to do is cover all of our cases. So we've seen how to convert many to many. We've seen how to convert many to one. We haven't seen yet the subclass relationships. What do we do here? So this is a weird one because dictionary inherits everything from book. So what do? Do I store a dictionary with, like, what is the key for the dictionary table? Well, could I say ISBN and title and whatever? I mean, I don't want to have to store every attribute separately. So what do? Okay, well, first I store the book table as usual. I make a table with a column title, publisher, year, pages, and ISBN. I make ISBN the primary key. And then what I do is for dictionary, I make a table that includes all the attributes that are unique to the dictionary object, so language in this case, plus only the primary key of the parent entity. So in this case, it would be this, because that's enough. If I know the language that goes with a given ISBN number, and that's in a table called dictionaries, then I know this ISBN number must be a dictionary, and here's its associated language. So I'd have this. And you might notice that if something appears in the dictionaries table, then it is a dictionary. Whether it's a dictionary or not is only determined by whether it's in that table. There's no separate flag that I have to set. And as usual, as usual, I have a foreign key. But in this case, my entire primary key has been borrowed from the parent entity. We saw already, we do not define key columns on child classes. No matter how far down they are in the hierarchy, we only define a key on the absolute root of the is hierarchy. We might see cases like this where we've got a relationship that has roles. So we saw this example in part 2. And here we have a bit of an issue because, think about it, if I try to encode the relationship into a table, I'm pulling in the key of the user entity twice. So what I have to do is I have to make sure that I pull in basically 2 copies of the key represented with separate column names. So I'd try this. I'd say, okay, well, the user's key is called account. So I'll make a column called the follower and a column called followee, and those together, because it's a relationship, the combined keys of all the endpoints, the follower endpoint, the followee endpoint, those become the primary key. And then I define the foreign keys. So follower references the account parameter of user, and followee also references that parameter separately. They're independent, but they both happen to be a foreign key on the same table. And then there's this. So in this case, notice how here the only key column in users was this account column. So there's only one column. This becomes a bit of a mess if I have a multi-role relationship that actually has an attribute, but also the product entity has a 2-column key. So you can see this is, I mean, we're really getting up there in complexity, and we need to make sure I prove the point here. The conversion is still the same. Okay, so one end of the contains, notice how I haven't even called it contains. I've actually called the relationship ingredients, because I think that best captures the amount of, I guess, the purpose of the relationship as opposed to the verb that I would use for it. Okay, so I've got the ingredients name and I've got the ingredients supplier. That's one product. Then I have the item name and the item supplier. So just to clarify, now that we have the table up, what am I actually describing here? So I have a product like bread, and it contains an ingredient, which might itself be a product like flour. So I want to know how much of this ingredient, flour, appears in this item, bread. But notice that both flour and bread could be products that are sold by some supplier. And the same thing is true of a lot of products. You might, if you were maintaining an inventory of products, you might actually want to determine how they were produced and what ingredients they contain. So here I have this weird relationship that ties an entity back to itself. And then I guess, if flour appears in bread, how much of it have I added? Okay, well, that's the amount. So I've got ingredient name, ingredient supplier. And then I've got item name, item supplier. So this is describing what appears in the item. This describes what item it appears in. The amount is some real number, I don't know, in grams or milliliters or something. And then I just go and add the keys. So it's a relationship table. So the keys are the combination of the keys from both of its endpoints. The key that I get from this, the key that I get from this. So that would be all four of these things, but not the amount. And then I have to define foreign keys. So how did I get these foreign keys? Well, I pulled in the keys of the products table via the item leg of the relationship. Okay, so that means that item name and item source is a foreign key into products. And I pulled in the keys of product via the ingredient relationship, and so they are a foreign key as well. Maybe that is a pretty convoluted example. What I hope I'm proving with that is that actually the conversion is the same as before. And in fact, this conversion is the same as the first conversion that we did. All we did was take the endpoints of the relationship, so the takes relationship, grab their keys, put them in a table together, fold in whatever came with it, and then define foreign keys. It's true that it looks a little bit more complicated if it's a relationship that doubles back on the same entity, but the conversion is exactly the same. We might have to take some liberties with column naming, but if you think about it, we were already doing that. We didn't call the column ID in the other example, we called it student ID. We didn't call it code, we called it course code. Same thing happens here, and even in this extreme example, the same thing happens here. So we actually know now that if we model the data correctly, the visualization, the ER diagram gives us a great way of looking at what we have, understanding relationships between the pieces of data that we're working with, understanding what is an entity unto itself, what is a relationship. Once we have that, we actually have a pretty mechanical way of turning it into tables, and it turns out that what we end up with, and we'll revisit this later, but what we end up with is actually pretty well normalized. Usually what we come up with is in a high normal form, so 3NF or higher. And that means that we don't have to spend so much time picking it apart. And if we end up with any normalization issues, which can still result in some cases, they tend to be very local and they can be resolved easily. We actually end up with a nicely distributed set of tables where any small fixes we have to go in and do aren't going to consume too much of our time. And so we already have a good decomposition of our data. So this actually takes us to the end of our direct discussion of ER diagrams. We're going to see them come up over and over again later as we understand databases. If we're going to work with performing queries or something, having an ER diagram of the top-down view of our data can be helpful. But we can now move, now that we've worked on when we have data, how do we normalize it? If we don't have data, how do we organize the data? And then how do we convert that to a set of tables? We're now finally ready to begin, which will be the next segment of the course after exam 2, the discussion of now that we have a way of representing and organizing it and we can put data in, how can we begin doing work with the data, even as the data sets become massive? And of course, that'll be the 3 weeks or a month that we spend talking about how to write SQL.